Good morning, students. Uh, I was beginning to wonder over the weekend if we had hit summertime, but I guess we're back to springtime. It's 50 degrees now. So again, the excursion through all the different temperatures, but it's amazing, when we have the warm temperature, even though yesterday morning and early afternoon it was cool pretty much, you still have that buildup of heat. And so it doesn't feel cool. So, I mean, it takes us a while to adjust. So I don't know. I think it'll probably warm up again, but we'll have maybe a little bit cooler weather than sometimes during the week than we did last week. So uh, never a dull moment. I know I talk about the weather all the time, but I think it's amazing. It interests me like mathematics. Maybe in a future life or former life, I was a meteorologist or something. And of course, if you do meteorology, you definitely have to know vector calculus. So it's a very much a STEM major. And my graduate school, Texas A&M, has a premier school of meteorology. And I think I do recall when I was tutoring in grad school, I actually had a student who was in that department, and they belly ached about how difficult it was. I said, well, that's a big field, and again, not that many people go into it, but it's certainly a wonderful STEM career. So just to remind you, I will do some more review exercises on Wednesday for the test. I know in some cases it probably gets kind of boring, but I think it's good just to give you that opportunity to just revive some of the ideas that we've talked about and to get you more ready for the test. And so if you have plans for Good Friday, then go ahead and make your calendar up so that you can get the test done on Thursday. I know some of you like the flexibility of still having Friday. And so, of course, the window, like I say, it's the same as it's been for the first two tests, the Thursday and the Friday of this week. So make sure you go ahead and choose a time that's going to fit best with your schedule. Now, today, of course, we're going to cover some other topics that will not be included on the test. Like I always say, as we do new topics, they may help you understand what we've done before. So don't look at this as being a hindrance. If some of the things we talk about today illuminate some other things, then that'll be very good. So let's go ahead and get started. Let me share my screen. Now, with the new material, or at least what follows the integral test, what I've written here is use knowledge of other series. So what we want to do with today is maybe not do more examples and maybe not a whole lot of proofs. What proofs I don't always get to, you can certainly see in my lecture notes. And it's only because sometimes the proofs are very straightforward and you get more experience by looking at examples. But in cases where, we need a proof just maybe to illuminate some ideas, I'll certainly do it. I always find that students feel much more secure with series as long as they know how to apply the results. So the first test that we will do today will be the comparison test, and then we're going to say something about alternating series, which I think you'll like because they're very interesting. So the first theorem is the direct comparison test. And it's pretty straightforward, direct comparison test. And we're going to use some logic that we've used before. And so that will make it fairly straightforward. Now, with the comparison test, we will all, just like the integral test, we're going to start with positive term series. So these nth terms, or these generating sequences, will be positive. That's always important when you're talking about series. Now, the statement is pretty simple. This is a very simple application of the monotone convergence theorem. Now, if we have an inequality that exists this way between the nth terms, that is the a sub n is less than b sub n, and the series generated by the b sub n term, n equal 1 to infinity, converges. If this series converges, then it forces the series generated by the a sub n nth term to also converge. Basically because the terms are trapped between the terms of b sub n and 0. So there's really nothing for the series to do except converge because it's bounded above. You know, we've got a bounded monotonic uh, sequence of partial sums, so it must converge. So that was the proof right there. So then n equals 1 to infinity, a sub n converges. Now, the thing that's useful here is that we definitely have to come up with an inequality, which can usually be very straightforward. Sometimes that's where you have to do a little bit of checking and jump out on a limb and see if it'll get you where you want to go. And then also we'll use what we know about other series, like maybe a geometric series or a p series, to use as a source of comparison. Now, the second part is actually logically equivalent to the first. That is, we don't really have any new ideas. Remember when we said that if a series converges, its nth term must have limit 0. Okay, I've had questions about this. If a series converges, like if we have b sub n series generated by the nth term b sub n, if this series converges, then we know the limit of b sub n is 0. We know that. Okay, to make it more useful, we take the contrapositive and we say, if the nth term does not have limit 0, then the series diverges. So just remember, if you just look at the nth term and see that it goes to 0, that says nothing about convergence. That's not what the theorem says. And some of you are still trying to hang on to that. And I've said many times, that's not what the theorem is saying. So be very careful that when we do these results, that you put these things down on note cards and look at the lecture notes and all and all the ideas that I've tried to emphasize, because that's extremely important. So how would that affect what we have here? Well, let's flip it around. If we're just going to change the hypothesis and the conclusion, so we'll do the contrapositive. And now we're basically getting this series that's generated by this nth term diverges. Diverges, then the series generated by the nth term b sub n also diverges. So this is nothing new mathematically. It's just a more convenient way to state number one. So again, when we take the negation, remember, and I've said this many times, P implies Q is logically equivalent to not Q implies not P. This is what we call the contrapositive. And so if we take the negation of this, we get this series diverges. The negation of this means the series with the nth term b sub n diverges. And so that basically says the negation implies the negation. So again, you flip it around to the contrapositive, and let me write that, contrapositive. When we study calculus, it's just basically a study in logic and how the arithmetic and the logic fit together to give us interesting results. And so now we're thinking, okay, so just like the result that I mentioned before about the nth term having limit 0, this is a similar construct. So basically, we don't add any new mathematics, ladies and gentlemen. We just rewrite a result in a way that's useful so that we basically get 2 for the price of 1. Now that's called the direct comparison test, and we'll do several examples of those. Now, the other type of comparison test, which is also very useful and has many applications, I want to state that, is called the limit comparison test. Limit comparison test. Now, just like we had before, we suppose that we have positive nth terms. Again, these are positive term series. Now, if, and this can be done in either order, the limit as n passes to infinity, and we take the ratio of a sub n to b sub n, or you could flip it. It doesn't matter. It's not going to make any difference. This has unique limit L, where L is positive. Then the series that are generated by these nth terms, n equal 1 to infinity, a sub n, and n equal 1 to infinity, b sub n, exhibit the same convergence. I've kind of changed the way I've stated this just to make it a little bit more cogent. When I say they exhibit the same convergence, they do the same thing. They either both converge or both diverge. So both converge or both diverge. Now, you can adjust things and come up with other convergence tests that are similar. But these two tend to be some of the most useful, and they'll be what we focus on. At this point, as you take more mathematics and you do more engineering science and physics, then you may adopt some new divergence or convergence theorems that may be suitable to a particular study that you're doing. Lots of times when a study involves a type of mathematics that recurs over and over, you make an adjustment so that you can make your work more efficient. But with that said, we'll try to focus on these two for our, voyage through Calculus 2. So again, these, just like the integral test, the telescoping, the geometric, these are very important theorems. And there'll be a summary of these in section 6 that will be very useful to you. And I will allude to that several times, and you can go into your ebook and print that out if you like. It's like having an integral table, but it's only one page as opposed to several. So let's see how these work. Now, I will say this. Students will usually tend to like one over the other. And unless, like for instance, when I give you a test, I might say use a particular convergence test. If I don't, it's like doing an integral. It's basically doing an integral, so you can utilize whatever technique that you would like as long as it's legitimate. It's kind of like the last test where a lot of you used miscellaneous substitution as opposed to integration by parts, which is fine. I mean, I've nothing wrong with that. If I really do want to see a particular technique, I'll say work this problem with this technique, so I can just see that you understand it. But let's just face it, as you move through your classes, there'll be less and less restrictions because you're just going to get to an answer that's correct and move the problem forward. So let's look at a lot of nice examples of this. I think you'll enjoy this. So again, we're not starting from ground zero, so to speak. we're looking at a series and then we're thinking, what can we do in this particular case to use what we already know? And this is where you just basically think geometric, maybe even integral test, and definitely the P series, because the P series give you those uncountably infinite number of infinite series that either converge or diverge. So when you look at a series like this, again, ladies and gentlemen, this is a positive term series because n is greater than or equal to 1. And so I was speaking with one of your classmates, and we were talking about limits and thinking about dominant terms. So when we start using these particular convergence tests, dominant terms are really going to come into focus, just like you did the limits at infinity with the horizontal asymptotes in calculus 1. Because when you look at a polynomial, the leading term is what dominates. The rest of the terms kind of fade, as in basically do fade as n passes to infinity. So again, this is what we want to think here. When we look at this particular uh, nth term here, we see that this n square kind of just stands out to us. The 2 really doesn't have much of an impact. So we would look at this and think this probably converges because this is kind of like the P series 1 over n squared. And of course, 2 equals P is one of the convergence restrictions. So as P is greater than 1, the P series converges. So we want to think convergence. So when you do this, it's really a proof. If I don't always write proof, that's basically what we're doing. So what we can do is observe something about a P series and how it compares to this. Now at this point, I will say there is nothing unique about what I'm going to do. And this is what you have to set out to do. And then sometimes WebAssign will just guide you through this. So that even makes it easier. So first, when we have 4 n greater than or equal to 1, and this is very simple, n squared is less than or equal to 3n squared plus 2. Now this is an elementary inequality that is clear. You can always use elementary inequalities and reciprocate them as long as you're using techniques that are logically clear. When they're not logically clear, you can't just kind of wash over them and say, oh, well, that looks like it's right. That won't work. And maybe we'll have to use some calculus like we'll see in some of the later examples. But when we look at this, if n is greater than or equal to 1, and this is kind of inductive, clearly with n equal 1, this is always going to be an upper bound. So we can easily write this just using basic arithmetic logic. Now, what we notice is that this is an inequality of positive terms, and so it can be reciprocated. So equivalently, 1 over n squared. And what I'll do, I'll put this one first, since it's gonna be the lower bound. Let me do this one first. So we're gonna have 1 divided by 3n squared plus 2. And this is clearly positive because these are positive terms. And then, of course, we will have an upper bound now of 1 over n squared. So this is the reciprocal rule. I teach this in college algebra or pre-cal, and it's amazing. It's a beautiful result that has many ramifications in integral calculus and the study of series. And so now when we look at this, we're thinking, well, this looks just exactly like the hypothesis that we have in the direct comparison test. So now we can look at this and say, well, this is something we know about. We can say that the series, in this particular case, n equals 1 to infinity of 1 over n squared converges. This converges because p equals 2. So basically now what we can see, and I'll just write this down, even though we won't have to do this every time, it's kind of overkill. So basically we're seeing that a sub n is 1 over 3n squared plus 2, and b sub n is 1 over n squared. Now, of course, that's that's a lot of detail, and I would certainly be glad to see detail on your test. Uh, Never an issue with that. But if you gave me this inequality and then you purported that this particular series with this nth term converges because it's a convergent P series, then you can say the given series by allusion to the direct comparison test would therefore have to converge. So then you'd say then the given series n equals 1 to infinity of 1 over 3n squared plus 2 converges by, and we can always abbreviate this when it makes sense, direct comparison test. So like we use IT for integral test, as long as it's clear and this isn't an abbreviation for something else that we use, this is more than adequate. So what you can see here is that there's really no unique path to utilizing the direct comparison test. What I used here was just something that was very simple. So for instance, maybe we have a comparison series, and we have to maybe justify that it converges, maybe using the integral test instead, or maybe we have to justify that it converges using the geometric series. It will depend based upon what the given series is. So don't feel like, well, if you have to do some extra work to motivate your argument that you're doing something wrong. That's perfectly acceptable. So don't, again, a lot of students think, oh, well, if I'm doing the series test, it's got to be quick and fast. Not necessarily. Not necessarily. Think it just like doing integration. Sometimes it's, very quick. Otherwise, you may have to do a trig sub or a partial fraction decomposition, and it takes longer. That doesn't mean that your approach is bad. So always look at this very methodically, just like you look at the integration problems. And then as you do several, you'll develop confidence with this. Now, let's look at another one. Not everything, like I say, uh, what you're going to find when you use these tests is that when you look at the series, you're going to think, oh, that probably diverges because that's like the harmonic series, or that probably converges because that dominant term is going to mimic a convergent P series. Or you can say, oh, look, we have R that's in absolute value less than 1, that dominates, and oh, that's probably going to converge. So you'll be able to look at the series and be able to figure out maybe some kind of path. And that, of course, would be obvious that you would have to do that. Just like with integration, you have to look at the patterns and see what technique will be the best. So here, let's look at another example. So we have n equals 2 to infinity. We have the natural log of n. So usually when I do natural log, I'll do like a cursive n and then the argument, a script n. So it's clear. I don't want to write ln and it look like two variables. So that's what I'll do for that. And then we have n plus 1. Now, this is where we think in this particular situation, what's the best way to approach this? Because when we look at this, we're thinking, if we think L'Hopital and how we work with this, um, the n, or the power function n, always grows faster than the natural logarithm. And so we're thinking, maybe this is going to mimic more 1 over n plus 1, which is kind of like the harmonic series, but we would have to use maybe the integral test to prove that. So we want to look at this and we want to think divergence, just because of the fact that the n plus 1 grows faster than the natural log. Now, so I'll write here, think divergence. Now with the proof, we want to do this in a very straightforward manner. So notice, we know that the natural log function increases it's an increasing function. And so as we bump up to 3, the natural log of 3 is actually greater than 1 because natural log of e is 1, and 3 is certainly greater than e. So we could say for n, here's one way to look at it possibly, n greater than or equal to 3, we would have 1 is less than or equal to the natural log of n. Now, you're thinking that's so simple, you didn't need to take calculus 2 to figure that out clearly. But here's what's interesting about this, ladies and gentlemen. This sets us up for success because now, remember, we can reciprocate inequalities as long as the terms have the same sign. If we multiply an inequality by something positive, we preserve it. So we have all of that machinery available to us. So now you can see what I'm going to do, if and only if. And so now we have 0. We've got 1 divided by n plus 1. That is, we're going to multiply by 1 over n plus 1 and do the same here. Natural log of n plus 1. Okay? So when we look at this, we're thinking, okay, this is what we're trying to figure out something. And here we have a rather simple nth term. And so we're thinking, oh, we can make quick use of this with the integral test. So now we can say f of x equals 1 over x plus 1, which is x plus 1 to the negative 1. Now, first, we'll say f is positive if and only if x plus 1 is greater than 0, if and only if x is greater than negative 1. Okay, so that certainly pulls in x greater than or equal to 1 from the integral test, so that's going to work. Now, we'll say f is continuous where it is defined, f continuous for x living anything except negative 1, negative infinity, negative 1, union negative 1 to infinity. So again, we're getting checks here because, of course, that includes x greater than or equal to 1. And then, of course, f prime, we can easily use the power rule, negative x plus 1 to the negative 2, which is 1, negative 1 divided by x plus 1 quantity squared, which is clearly less than 0 for x living between negative infinity to negative 1, union negative 1 to infinity. So this implies f decreases there. So check. So all of that was the hypothesis for the integral test. And so you're thinking, you know, that would be a quick check. Again, when you use the integral test, you've got to do a quick check of these things, even though it seems pretty obvious in most cases. That's all right, but you need a quick check. And then now we can say, all right, well, we think it's going to diverge. So we're going to look 1 to infinity of dx x plus 1. So now, of course, this is the limit as well. Let me use another letter. We'll use b. I think we usually use b. b approaches infinity. 1 to b dx x plus 1. So this will be the limit as b approaches infinity of the natural log of the absolute value of x plus 1 evaluated from 1 to b. And so this gives us the limit as b passes to infinity. So we'll have natural log of the absolute value of b plus 1 minus the natural log. Of course, replace x with 1. So that'll give us natural log of 2. It's still an absolute value if you like. But notice in this case, we've got an increasing function, so this just diverges to infinity. So this took a little bit more time. This wasn't a P series, so we couldn't just say, okay, P equals 1/2, and so it diverges kind of thing. You're thinking that this takes a little bit extra time because we had to apply the integral test. So now we see this implies that the series in this particular case here, n, and we, again, we just start at 2, n equals 2 to infinity of 1 over n plus 1 diverges. Now, when we look at this argument here, we're basically starting here at 3, so we can always just write down the first term. Then we can say, if you want to do the n equal 2 term, this will be log of 2 divided by 3 plus n equals 3 to infinity, natural log of n plus 1. So this is just basically hinging on the fact that if you just got some straggling finite terms, it's not going to change anything. But just to break it up is technically saying that we're really focused on this part, and that's just a finite number. You could have a million terms, and that's still finite. Okay, but just to be technically correct, this now can be broken down into these two pieces, and these are all the pieces for n greater than or equal to 3. And we'll say diverges by direct comparison test. So in comparison to the last one, we see here that when we drew our inequality, we were thinking divergence from the beginning because of the 1 over n plus 1 and the fact that the natural log doesn't grow as fast. So we're thinking it possibly diverges. So this is a lot more technical than the previous problem. And so with that in mind, we're thinking, well, how can we basically create a lower bound for the given series that will get us where we want to go? So we start with this very simple inequality and then multiply by 1 over n plus 1. And so now we can analyze this nth term. What does it do relative to an infinite series, where we verify the hypotheses of the integral test, and then when we actually pass to the improper integral, we see it diverges. And of course, the integral test is very robust. And so, of course, the divergent improper integral then is equivalent to the divergent series. So this diverges, and therefore, as a lower bound, this basically blows up. So there's not much hope for this nth term. It's going to have to do the same thing. These are positive term series, so there's nothing good that's going to happen to this one. So that's where this contrapositive form is very useful to us, and we see it in play here. So therefore, we can now show that we have proven that this particular series diverges, and we have done that using the direct comparison test. So what you're going to find with these types of arguments is that they really make you better analytically. That's one thing in Calculus 1, when I teach that, I really strive to help everybody build the level of analytical mathematics so that when you get to Cal 2 and you've got to do a lot of arithmetic, there's at least an undergirding for it. And so we see that here we're spending more time with arithmetic, but we're putting in all these other calculus ideas that we learned in Cal 1 that allow us to use the integral test. So very good. Let's try another one. Now, what I want to do is I've got all of these examples with the direct comparison test, and I'll do some more of those. But before I do that, let me just throw in a limit comparison test, just so you can see that. Limit comparison. So here's an example. Now, I was talking with one of your classmates, And I said, the classmate said, "Oh, math is fun." I said, "Well, it's fun when you know what you're doing." And I like doing math. I like doing research, but it's not always fun until you get to that point and you start feeling more confidence, like the work you're doing is going somewhere. So just look at this as something that builds your confidence. So like working on integrals, you build your confidence and your anxiety comes down a little bit. So here's an example. Yeah, here we go. So we've got n equals 1 to infinity, 5, and then we have 4 to the n plus 1. So this is what I was talking about. Sometimes it's nice where you've got a comparison series that's a little bit simpler and you don't have to work as hard. Now, this is what I was saying before. When you look at all of these terms, you see the 5 is a constant, but downstairs you've got the 1 and you've got 4 to the n, which is going to dominate. And so basically 1 over 4 to the n is what this is starting to mimic if you just multiply it by 5. But multiplying by a constant is not going to really change convergence. That doesn't do anything. So we're thinking here that this is looking really good. So at this point, I'll go ahead and state this. Our A sub n, like we were writing the theorem, is 5 divided by 4 to the n plus 1. And then we're going to think, okay, the dominant term here in the denominator is 4 to the n. So that means let's let B sub n be 1 over 4 to the n. Okay? Let's look at that. And then we can do a comparison. Now, why do students tend to like the limit comparison better? Because it reminds them of sequences and limits. It reminds them of calculus 1, and everybody loves limits. Limits are fun. Well, they're easier than integrals. And so now when we look at this, we say the limit, this is why I wrote these down, because we can just go ahead and write down the hypothesis of the theorem. That would be A sub n over B sub n. So we have the limit as n passes to infinity. Now remember, this is reciprocating the B sub n, so you could go ahead and invert and multiply. So this will be 5 divided by 4n plus 1, and then we invert and multiply. So this just gives us 4 to the n divided by 1. Okay, so that's how we can get the ratio. You can do the complex fraction, but if you like, you can go ahead and flip it, your choice. Usually it's a little bit simpler to do that. And this is a very straightforward computation that will save you just a little bit of time. And so now you can see the 5 can be factored. So we have the limit. Now this is starting to look like a polynomial. So we have 4 to the n, and then we have 4 to the n plus 1. So now, if you will, we can think about factoring the 4 to the n, because that will absorb, or we just doing like e to the x, divide by e to the x numerator and denominator. So now this will give us 5 limit as n approaches infinity. So divide by 4 to the n upstairs, that'll give us a 1. Here, that gives us a 1. And then, of course, this will just be 4 to the negative n. So the idea, and let me just write this down. This is something we do all the time. We have 4 to the n, 4 to the n plus 1. So multiply and divide, you can just say, just multiply by 4 to the negative n, divided by 4 to the negative n, if that's a little bit easier to write. And so the laws of exponents give you 1, again 1, and then plus a 4 to the negative n. So that's just a little quick sidebar of what we did here, which we've done many times with e to the x when we couldn't find a nice antiderivative. Now, of course, when we look at this, this will just converge to 0 when we pass to the limit. These are fixed. And then, of course, 4 to the negative n is a decreasing function. So this converges to 0 using the properties of the exponential functions. So now passing to the limit, this is 5 times 1 divided by 1 plus 0, basically the quotient rule, and this is just 5, and that's certainly a positive number. Okay, so the limit comparison test, you might be thinking, could I use L'Hopital? Absolutely. If you get to a limit that requires L'Hopital, again, you don't have to change to X's if you don't want. It's permissible. Go ahead and use L'Hopital, especially if you have infinity over infinity or 0 over 0. Go ahead and use that. That is certainly something that you can utilize. So now we say, okay, let's go back to B. Let's go to that nth term and see what that series looks like. So we have 1 over 4 to the n is the nth term, but of course we can rewrite this. You knew this was an allusion to the geometric. So we just have 1 over 4 to the n. But of course, this is an R in absolute value less than 1. So this series converges. So we'll just say converges. And we'll just say geometric test. That's such a useful series. The geometric series is just wonderful, and we will see more use of it. Now, like I said before, we see that the limit is a positive number. So both series exhibit the same convergence. So if this series converges, so does this one. So this implies then the given series n equals 1 to infinity of 5, 4 to the n plus 1 converges. I know it, I sound like I'm a first grade teacher. Converges. I'm just trying to focus on the terminology, okay? You know, it's sad when you have students that when I was on campus, when we were back in the former world, students would say, Professor Ron, and they'd be in other calculus classes and they'd say, what does it mean for a series to converge? I said, well, do you even know what a real series is? Well, not really. I said, well, then that's the problem. Let's figure out what it is, and then we can talk about convergence. So I'm focusing on the terminology to make sure that you get this, because these are the rudiments. These are the rudiments, and they're extremely important. So, because when we get to power series, we'll have to drag all of this stuff with us because we'll eventually have to use it. Now, so this converges what? By, and we can use the abbreviation limit comparison test right there. So think of real series kind of like an open book. That is, when you work with them, you're doing, it's like doing an integral problem. You think, wait a minute, I've got to look for a pattern here because I have certain techniques that I know. Okay, just like we have certain convergence theorems that we know. That's all we have. So we can think of the convergence test as an integration table, just a set of tools that will allow us to attack these problems. And so sometimes we have to work a little bit harder, but that's okay. And as you do more and more, then you'll develop some additional confidence. So again, this is very similar to what you've been doing with the integrals. So let's see here. I want to do one more with the limit comparison. Yeah, let me do this one. So again, not overly difficult, but a little bit different. Okay, a little bit different. And so again, just remember all of the rudiments that we have covered so far, we will use over and over again. So when you're not quite sure, go back to the beginning and just kind of build up to the problem. And that way you'll make better choices. So let's look at this one. So again, you can make up these problems. Once you do a problem, make up your own that mimics the last one you did. That'll build confidence too. So we have n equals 0 to infinity, and we have the square root of n squared plus 1. Now, when you look at this, this is similar to a technique that we've already used. Think about polynomials, and you can find some really interesting theorems based on polynomials in the P series, and there's a problem like that in your WebAssign that I think you'll find to be very useful. And it covers the ideas. It's like a problem within a problem. Now, when we look at this, we look in the denominator and see that the n squared dominates. The one really has no impact as n passes to infinity. So basically, we've got 1 divided by the square root of n squared. Of course, the square root of n squared is the absolute value of n, which is n since n is positive. So we're thinking when n becomes large, this nth term is really mimicking 1 over n. Okay, so now we can say, we know a sub n is 1 divided by the square root of n squared plus 1. And then we can let b sub n just be 1 over n. Again, what we're trying to do is make a comparison nth term based upon what this is going to do or what it's going to actually mimic as n becomes large. So we want to compare the given series with a new series. So we look at the nth terms. So again, we see in all these cases, these nth terms pass to 0 as n passes to infinity. But that doesn't say anything about the convergence. Okay, that's the main thing here. We don't have that luxury. Boy, if we did, there really wouldn't be much work involved at all, and maybe this wouldn't be very useful. So now we can look at this and say, okay, now let's pass to the limit. So we'll have the limit as n approaches infinity of a sub n divided by b sub n. So we've got the limit as n passes to infinity. Now, if you like, we'll reciprocate like we did before. So we have 1 over the square root of n squared. We can always factor, or we can use the laws of exponents. Whatever technique you use, as long as it's legitimate, I'm fine with it. It just has to be good mathematics. And don't leave a big old space in your work anymore, because if you do, I'm going to count all points. I've got to see the logic. I've got to see enough so it's convincing to me that you understand. Now, notice as we reciprocate and multiply, we basically have n over n. So if you want to kind of couch this all together with the radical, we can just re-express n as the square root of n squared, maybe as a technique to evaluate this limit and use continuity. But of course, you can factor under the radical too and do that. Same difference. So we can just say this is the square root of n squared over the square root of n squared plus 1. But now we can use the laws of exponents. So this is the limit as n passes to infinity of n squared divided by n squared plus 1. Many different ways to do this. I just thought I would introduce this as an alternate. Again, you can factor under the radical or do this, but now we can use the continuity of the square root to pass the limit inside. So we have the limit as n passes to infinity of n squared divided by n squared plus 1 to the 1/2. But now we have a very simple limit here. We have dominant terms of n squared, and the leading coefficients ratio is just 1. So now we see the limit of the rational function here is just 1. So we have 1 to the 1/2, which equals 1, which again is a positive number. So we have the L in this case, which is 1. And so now when we go up here, we go to our friend, n, well, of course, we're not going to start at 0, so we'll do 1. Again, I won't be so picky this time. If we have a few straggling terms, it doesn't matter. What is it? You know, you infinity plus a billion is still infinity, or you know, or if you've got a convergent series, you can add a billion to it and it still converges because a billion is a finite number. So if we do n equal 1 to infinity of 1 over n, this diverges. We know this. We've already proven this. This is the harmonic series. We proved this using the p integral. and the integral test. So this is the harmonic, very useful. We've already used this harmonic series. And so if we know that when we compare the two nth terms that we get the limit, positive limit here, and we know that one of them diverges, we know that the other nth term must create a divergent series because they exhibit the same convergence. Then the given series, n equals 0 to infinity, well, divided by what? The square root of n squared plus 1 diverges by limit comparison test. So what we're seeing in this particular case is kind of the repetition of the same idea. Students will say, well, it's kind of like the first time you did integrals, you think, oh, I don't know what to do. What am I going to do? And then your professor says, well, this is all you have. So you either use the power rule or basic substitution. Otherwise, you don't worry. They got two processes. Now, of course, we've got more techniques now, but we still find ourselves going back to the basics. So when you now look at these series, you know, you don't think, well, let me just add up a bunch of terms and see if I can figure it out. Well, that's not going to work. That will never work. Okay. We analyze things arithmetically, but we have to apply basic fundamental theory. So when it comes to limit comparison and the direct comparison test, we're either looking at an inequality or we're looking at the limit of a ratio of nth terms using what we know about one of the series. So for instance, if we use the comparison test, we have to be able to figure out something about one of those nth terms, how they react in the infinite case. Otherwise, we have no source of comparison. So when you say comparison test or limit comparison test, that means you've got to bring to the table a series whose convergence you know, or whose convergence you can determine fairly easily. Because it's like doing integration by parts. I mean, you don't integrate something that's more difficult than the original problem. You square things off so that whatever you have to integrate is something you know how to do. So this is analogous to that. And of course, it's not always straightforward. And of course, there's more than one way to do it. But in most cases, you're going to look for the simplest route. All right. So comparison test, direct comparison test, limit comparison test. These are your friends. So look at these as a positive light, so to speak, that actually help you arithmetically to deal with series. Now, the other type of series that kind of takes us maybe over to the other side of the fence, but we're still drawing on what we already know, is the alternating series. So the alternating series. Now, when, you know, all of you physics masters and those of you that love physics, I know there are plenty of you. I mean, that's probably why you're interested in engineering. Like I always say, I had an interview with my boss last week, and I talked about the fact that my study of science is what made me realize my interest in mathematics. I always had the interest in math, but science was just such a wonderful way to cultivate that interest. And so as I go over to the math department to learn more mathematics, I just eventually stayed. But the beauty is that when you have this knack that a lot of you do for inventing things as engineers or computer engineers, you use math as a tool. So again, think about this as just additional ideas that you can use to solve problems of interest. And so it's always good. It's kind of like learning new vocabulary words. You can try out new words in your next English paper and feel good about that. I mean, again, one thing that sometimes makes me a little bit sad is that things I used to study, I don't have time for now. And so when I think about them and try to do them, it's rough. And as you mature and you work into your professional lives, there'll be certain things that you're not going to have as much time to do, and so you're going to have to pick the things that are the most important. But like Professor Ron, you're stubborn and you want to do everything. So don't do that. Now, for the alternating series, what we mean is that the terms of the nth term, that is the generating sequence, alternates in sign. So what we first do is we start with a generating sequence that's positive, an nth term that's positive. And then we create, just like before when we have positive term series, then we create the change in sign that alternates in a pattern. So we'd say n equals 1 to infinity, and we'll use this convention, -1 to the n plus 1, a sub n. So when we look at this, and this is one way to write an alternating series, ladies and gentlemen, remember series as the nth term generates, as n starts maybe at 1 and goes to 100 or whatever. It could well be the case that if it's not a positive term series, like maybe you got a trig function, you'll get some positive and some negative, but they won't be in any kind of prescribed order. This is very regimented. That is, when you look at this, you start with an nth term that's positive, okay? And then you see that the sign will alternate. This structure right here alternates the sign, because when n equals 1, we get a 2, so we get plus 1. When n equals 2, we get a 3, so we get -1. So it'll be plus, minus, plus, minus, plus, minus. So that's what defines an alternating series. The sign alternates in a regimented pattern. So we get a sub 1 minus a sub 2 plus a sub 3 minus a sub 4 plus a sub 5 minus a sub 6, etc. Now, we don't want to try to think about convergence by adding up 100 terms and keeping our fingers crossed. That doesn't work. We know that from Riemann integration. When we learned the fundamental theorem of calculus, I mean, that's never going to work. And again, that's not a proof. You have to be able to do things in a more systematic way that appeals to the theory. So now what we want to do is say, if we have some kind of structure like this, what is the ultimate test? Now, there are different convergence tests for alternating series, but the one that we will use will be the one that I'm going to state now. And then there's going to be a nice error estimate that you all will like, because it won't be as hard as the one with the integral test where you have to compute an improper integral, but we saw how to do that. So this is basically going to be the alternating series test. And I'm going to say something about the actual estimate to give you an idea how we work with these things. And then, of course, anything that I don't cover, at least from the theory point, you can look in the lecture notes to get some additional ideas there. Just again, the thing is that it's kind of hard for me to test you on proofs in the virtual setting, but what proofs I do execute in lecture, I consider to be very important. So those I want you to know. So alternating series test. Now again, suppose a sub n is positive and the limit as n approaches infinity of a sub n equals 0. Okay? Now again, this is important basically because you're thinking if we have a convergent series, we would get that anyway. But notice here, now that the nth term is not this, it's all of that. So a lot of times when I do this, I'll take all of this, which is the nth term for the alternating series, I'll just call this u sub n, because the u sub n contains the alternating sign and the a sub n, okay? So now for this alternating series test, we have to kind of push away the alternating sign and just look at the positive term sequence, okay? So we need positive terms and we need this. We need that the limit of this positive term sequence is 0. If a sub n, and this is where we talk about monotonic, is non-increasing. This is a really odd test the first time you see it, is non-increasing. What does that mean, ladies and gentlemen? That means a sub n plus 1 is less than or equal to a sub n. And we just say eventually. I mean, you know, maybe it doesn't work for one or whatever. Usually it will, but we need it eventually. Kind of like we're doing the integral test and say, for instance, the function's only positive for 2 or greater. We can get over that as long as basically there comes a point where we've got the continuity, the degree decreasing, and the positive. So we don't have to worry about little things like that. We just need that as, you know, n passes out to infinity, all of those hypotheses are secure. So I say eventually here because, again, we don't need to be so picky that we paralyze ourselves. So if a sub n is non-increasing, then the given alternating series converges. Converges. So this is a very, very interesting result because we have a twofer here, and this is not surprising. What do we have to do when, I mean, one thing students like, well, I know that's an alternating series. It's like they see that and they're like, they smile because they're thinking, oh, that's clearly an alternating series. Then I just have these two things to check. And I'm thinking maybe they won't be so difficult. Sometimes they're easy, sometimes they take a little bit more time depending on how complicated a sub n is, okay? So this is like looking at inequalities. Maybe you have to use some calculus. It just depends on how complicated a sub n is. So we've got two things that we've got to do. We've got to show that this limit is 0, and then we have to show the non-increasing right here. So the alternating series test is like a little litmus test. We have a recipe that we have to follow. Now, one thing that's very interesting is the error estimate. I want to state this. And I'll say something about why this is true, and it'll have a direct impact on how we do this. This is also done the same way with the monotone convergence theorem, and this is called error estimate. So basically what we want to do is we'll just say let S equal the sum of this alternating series. That is, it converges. We'll just say converges. And then what we want to do is, like with the integral test, is use a partial sum to approximate it. So in this particular case, again, we need some other things too. We'll just say let S sub n be a partial sum. So remember, I'd said we don't have to switch to k because no ambiguity here. N equals 1 to infinity. Oh, how funny. N equals 1 to n with partial sum. It's not very partial if it goes to infinity. So we have -1 n plus 1 a sub n. So this is going to be our partial sum that we're going to use to approximate partial sum. Then if a sub n is non-increasing. So again, what's important here is that for this particular type of convergence, we need 1 and 2. For this error estimate, we have to start with a convergent series. So we're just given that. Start with a convergent series, and then we're thinking, okay, this will be the partial sum that will be an approximation. And as long as the a sub n is non-increasing, okay, we've got to have non-increasing, then we can get an estimate on the remainder, just like we did with the integral test. So the remainder for the n-term partial sum in absolute value will be the original sum, just like we used S for the integral test, minus S sub n. It looks the same, doesn't it? But now it's just like doing the improper integrals and all that. We're going to shave off the first n terms here, and then it's going to start at n plus 1. The uppercase n plus 1 to infinity. Oh, and here, let me write this out. You can see that. So now, when we think about this, we take away the first n terms, and then what's left is the a sub n plus 1, a sub n plus 2, etc. That's what's left. And here's the remarkable fact. This is no bigger than the first neglected term. And we can easily show this. So what we do is we say this is the first neglected term. I like that terminology. First neglected term. So when we look at this, we're thinking, say we used S sub 3, okay? Then we could look at the S sub 4 term, excuse me, the A sub 4 term, and know that the error here in using this approximation is no bigger than that term right there, and even most likely better. So students say, I'll take the alternating series any day. This is terrific. This is easy. I can remember this. So the key here is that all we have to do is basically look at this structure right here. So let's just go ahead and fill in the gap that takes us from here to here. It's really easy. So now we'll just take this right over here and just map out some of the terms. So why? So now what we can see when we have n plus 1, we'll go ahead and fill in the terms. We have negative 1 to the n plus 2. That is, n is n plus 1. And so, the uppercase, so we get n plus 2, a sub n plus 1. You can see how this is going to work now. Then we have plus negative 1, n plus 3, a sub n plus 2. We'll just write out several terms. Negative 1, n plus 4, a sub n plus 3, plus, I'll write out enough so we can do some factoring, so you'll believe me, n plus 5, a sub n plus 4, and I'll write one more. And then, of course, if we want to tack on some extra terms, it'll be clear, n plus 6, a n plus 5, etc. So this, by writing out a few of these terms, ladies and gentlemen, we basically see a pattern. Now notice, we can apply algebra to this, even though it goes on ad infinitum. What we see here is that we've got at least the n plus 2 in all of these. So we can now use the properties of the absolute value and factor this. So this will be negative 1 to the n plus 2. That is, now factor this out, or just factor it. And what does that leave us with? it leaves us with an a sub n plus 1. But now we're left with the minus 1, and then the minus 1 squared, and then the minus 1 cubed, and then this minus 1 to the 4th. So we get the alternating sign. So we get a sub n plus 1 minus a sub n plus 2 plus a sub n plus 3 minus a sub n plus 4 minus a sub n plus 5. Keep going, plus a sub n plus 6, etc. So what you see here, plus, minus, plus, minus, plus. The pattern is going to be exactly what we think of as alternating. So now let's finish it. I told you this one was pretty easy. That's why I want to go ahead and go through it. So now you're thinking, how do we use the non-increasing? We have a convergent series, but we've got to use the non-increasing. So now this gives us what? So we're going to factor it. A sub n plus 1, and now factor the negative here. A sub n plus 2 minus a sub n plus 3. So again, minus minus gives us the plus. Now factor again. A sub n plus 4 minus a sub n plus 5. And I'll just go ahead and do the n plus 7 term since you know it's going to be there. A sub n plus 6 minus a sub n plus 7, etc. But here's the beauty of this argument. This is a non-increasing sequence. So all of these are non-negative. Could be 0, could be greater than that. The thing is now this is an upper bound because we're subtracting from the n plus first term. So now we see this will be greater than or equal to the absolute value of a sub n plus 1, but a sub n plus 1 is positive, so a n plus 1. So now what we see is that we use the non-increasing, which is the same proof that you use when you're proving the alternating series test. But I thought it would be nice to kind of sandwich these together so you can see this really quite remarkable error estimate is now a result of the non-increasing. So when you're looking at an alternating series, you're thinking that's the best estimate in the world. The idea is that you can look at the terms, the positive terms, and say, well, that's getting small pretty fast. I won't have to use too many terms to get a decent estimate. So again, this is the first neglected term. When you write the partial sum, this is the term that's next in the sequence that you left out, the first neglected term. So you're thinking, I wish all series were this simple, but this is a elegant result using the arithmetic of the alternating series with this particular convergence hypothesis. So again, series can take on different forms, okay? We are focusing on convergence tests that are fairly conventional and that are used throughout mathematics. That doesn't mean that you can't make some adjustments and produce other convergence tests, okay? The thing about the alternating series, it's not very robust. I mean, if you have the hypotheses, you're fine. If you don't have a conclusion. Then you're going to hope maybe it diverges. You know, the beauty of this is that when we look at alternating series, we're thinking for the most part we'll probably, you know, grab the brass ring and be okay. But the divergence test always turns out to be very useful when we think about these particular tests. So again, alternating series, very unique, but very straightforward in terms of estimates. So let's do a couple of examples with these. Now, I have one other thing that I want to talk about with in terms of terminology, but before I do that, this will be absolute and conditional convergence. Before I do that, I just want to do a couple of examples, and then I'll come back to that idea. So the first neglected term is easy to use, easy to use. So here's an example that won't surprise you at all. So let's look at an alternating series. So this is n equals 1 to infinity, -1, n plus 1, divided by n. So just for grins, I'm just going to write this out. You know what this series is. When we have 1, we get the positive, and then it'll be plus, minus, plus, minus. So this is going to be 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6, etc. Let me put the minus in there. So this is what students and mathematicians term the alternating harmonic. So you're thinking we're taking the divergent harmonic series and we're alternating the sign, because you know 1 plus 1/2 plus 1/3 plus what, it diverges by the integral test. So now we look at this and say, okay, well, there's the alternating part. A sub n is 1 over n. And clearly the limit, now if we need L'Hopital, we'll use it. Don't worry, you don't have to change the x's. If you need L'Hopital, it's at your disposal. But this is a very straightforward limit. As n passes to infinity, this is clearly 0. So we've got 1 very, very easily. Now, the non-increasing is pretty simple. It's like the comparison test. First, for n greater than or equal to 1, we know that n is less than or equal to n plus 1. Now, of course, that's easy. When the general term, ladies and gentlemen, is so simple, we can use elementary inequalities. But when it's not simple, we may have to look at the corresponding real valued function and use some calculus, because I mean, you can't just say, oh, clearly. Well, no, mathematics requires proof. And so if we can't get at it with an elementary string of inequalities, then we may have to use some calculus, and that's fine. But that's the more honorable way to do it than to say, well, you know, it looks like it does that. Looks like and is and does are two different things. So now we can see we can reciprocate. So now we get 1 over n plus 1 is less than or equal to 1 over n. But of course, by definition, this is a sub n, and this is just a sub n plus 1. So clearly, we get a sub n plus 1 less than or equal to a sub n, and we have non-increasing. So again, that's a check. So we'll say the original series n equals 1. Then the series n equals 1 to infinity of -1 to the n plus 1 divided by n converges. Here we go again. By what? Alternating series test. Like I say, you're never going to have to work very hard with series that look like this. Why? Because it's like, okay, what test are you going to use? Well, unless it's a power series, you're going to use the alternating series test. So the key here is, and this is profound. It's just like, you know, again, when we look at series and we look at the nth term, we don't, when it comes to convergence, we have to be very, very focused. We can't just say, oh, this is what I think it is. The harmonic series 1 over n diverges by the integral test. But when we create the corresponding alternating series, we get convergence. So that alternating is the ingredient that we need to rig a convergent infinite series. So this brings up the next line of terminology. So let's look here. So for instance, say we have this. N equals 1 to infinity. And this is just a generic nth term, u sub n, and we take it at its absolute values. If this is less than infinity, then we say, that is, it converges, then we say the series n equal 1 to infinity of u sub n converges absolutely, in absolute values, absolutely, converges absolutely. So if we can slap absolute values on an alternating series or a series that does change sign, or maybe not, maybe there's nothing to be gained by this. But if this is true, that is, this is less than infinity, that is, it converges, they mean the same thing, then we say that the given series converges absolutely. Okay, then that's the first definition. Number two, if the given series in absolute value here, u sub n, does not converge, but the series without the absolute values converges. Then the given series converges conditionally. Converges conditionally. So that's what we just talked about. So converges conditionally, converges absolutely. And then the very last theorem is this. Absolute convergence, and this proof is easy, you can see it in the notes. Absolute convergence implies conditional convergence. So this result is actually very useful, and we will find tests for absolute convergence when we do the ratio test and the root test. Those will be monuments of real series convergence that we will hinge on. And again, we will use the fact that if we slap absolute values on it and we get convergence, then not only do we have this converging, but we have the series without the absolute values converging. Again, they may end up being the same if there's no sign change. Now, so when we look at this example here, ladies and gentlemen, we can use some of this new terminology. Notice here, and I'll write this, let me just put this on an extra sheet of paper to bring this home. So from the last example, we started with this. We had n equals 1 to infinity, -1, n plus 1 over n. So if we look at this, for instance, and then we'll just say, observe. Let's put the absolute values in. This is for each n equals 1, absolute value, -1 to the n plus 1 over n. So this, all of this is u sub n. Well, when we apply the absolute value for each n, the alternation goes away. So we have n equals 1 to infinity. So we have -1 to the n plus 1 in absolute value divided by n, of course, which in absolute value is n. And so for each n, this retires the negative. The absolute value absorbs the negative. So we just simply get n equals 1 to infinity of 1 over n, which is the harmonic series. Harmonic series, which diverges. So when we look at this, we're thinking, okay, well, this does not converge absolutely. So done with that. But we have this converges by alternating series test. We just proved that. So what we see now is that since the series does not converge absolutely, but it does converge without retiring the alternation in sign or the sign changes, we see that this series converges conditionally. Therefore, by definition, the given series converges conditionally. Converges conditionally. So these are just new terms. Now that we have alternating series, we can ride the wave. If we can prove that we have absolute convergence, then we don't have to check anything else because absolute will imply the conditional. So this is one of those things in calculus where you see an example that kind of looks like this, but the sign is alternating. We know there's no use to look at this anymore. This is the divergent harmonic series, but this makes an excellent example for absolute and conditional. When we have the alternating series, which uses the A sub n from the harmonic, then we get convergence. So this type of convergence has to be addressed. Basically, when we talk about integration, we do the same thing. We talk about absolute integration, integrating the absolute value of f, like you did in calculus 1. So the key here is that with the alternating series test, not only do we get a really great error estimate theorem, but then we get a way to characterize the series as positive terms. So we think, okay, well, if we just threw away the change in sign, would we get anything? Would we get any convergence? So we just test it. And then we add some new terms to classify what we mean by that. Now, let's go ahead and look at some more examples. Now, one thing that's interesting and what I wanted to do was give an example of where we can use some L'Hopital. Sometimes if we're trying to show certain characteristics, this is what I was saying before. Sometimes maybe the A sub n is too complicated. Maybe we can't just use simple inequalities to get to the results. For instance, for the theorem on convergence of absolute, of alternating series. So what we're going to do is apply some calculus. So let's look at this one. I thought this was an interesting problem. N equals 1 to infinity. And let's see here. So let's see, we've got -1 to the n plus 1 natural log of n plus 1 divided by n plus 1. Now, why am I doing this? Because this reminds us of a problem that we did before that we saw diverged. So this is an example that we already know something about. You know, so if we slap the absolute values on it, we have the example that we did before, and we know the result of that. So this is an alternating series. Now what we see, and this is important, when n is equal to 2, 3, 4, 5, the argument here, we certainly get positive outputs with the natural log, and of course positive outputs with the n plus 1. So we clearly get an alternating series. Now, with this particular case, we have A sub n equals the natural log of n plus 1 divided by n plus 1. Okay? So what do we need to show? We need to show that this limit is 0, and also for convergence, and also that the sequence is non-increasing. Okay, now this isn't as simple as what we had before, so the simple inequalities don't work. And if you just say, oh, it's obvious, well, that's not good enough. So now what we can say is the limit as n approaches infinity of A sub n equals the limit. We don't really have to switch to x's here. We can be a little bit less formal because this is just a sequential limit. When we do derivatives, we kind of need you know, at least for the increasing, decreasing. But that's again, what is basically what I'm allowing you to do here without having to switch back and forth. Now, when we look at this particular situation here, n passing to infinity, we have a increasing function. So basically we have the log which passes to infinity, and of course the n plus one which passes to infinity, if we're thinking about these as real variables. So here we can apply L'Hopital's rule. So with that, we'll take the derivative of the numerator and the derivative of the denominator. So I'll allow you to do this, even though, like I say, we'll usually switch to the x's. So here we get 1 over n plus 1. And then, of course, the derivative of n plus 1 relative to n, that's just 1. So we get the limit as n passes to infinity of 1 over n plus 1, which is clearly 0. So that's a check. So when you're applying L'Hopital with the sequences, I'm okay with not converting to the x's. Of course, when we use the integral test and increasing, decreasing, I think we can, you know, switch to the x's. But here I'll allow it because I think I do that in the notes, and it's okay. Technically, we're being flexible, but I don't consider that to be mathematically horrible, so to speak. So now what we want to think of is non-increasing. So let's look at the real valued function here. F of x equal log of x plus 1 divided by x plus 1. So when you look at this and you think about it, you say, okay, well, let's look at the derivative. So f prime, just apply the quotient rule. The derivative here will just be 1 over x plus 1 times x plus 1 derivative, which is 1. Of course, multiply by the denominator, minus the natural log of x plus 1 times the derivative of the denominator, which is just 1, divided by x plus 1 quantity squared. So that's just the quotient rule. Okay, let's just clean this up a little bit. Of course, these will absorb, and we have 1 minus the natural log of x plus 1 divided by x plus 1 quantity squared. So again, when we're working with derivatives and things outside of the L'Hopital's rule and the integral test, it's probably best to switch to the x. And if you want to do it here, you can, but I think we're okay there. Sometimes I'll be working and I'll just say, well, I'm just going to switch to the x's, but now I'm saying that's okay. So when we look at this, we say, okay, when would this be less than 0? Well, of course, this is non-zero or positive downstairs. So this is less than 0 if and only if 1 minus the natural log of x plus 1 is less than 0. So now it's like we're in pre-cal, right? So if and only if we have the natural log of x plus 1 will be greater than 1. So now we can apply the natural exponential function because it's an increasing function and it will preserve the inequality, or just use the definition of logarithm. So this will be x plus 1 is greater than e. So x must be greater than e minus 1. But of course, e is 2.7 relatively, so we've got basically 1.7. So this will give us what we need. So then this implies that, again, f of x decreases for x greater than e minus 1. Therefore, a sub n is non-increasing for n. And of course, this is like 1.7, so we can say n greater than or equal to 2. So that's what I was saying before. Eventually, it's what? Non-increasing. So it doesn't matter if it starts at 5 or heck, it could start at 5 million. Infinity is way out there. So the thing is, you can't be so particular. Oh, well, it didn't start at 1. This isn't gonna work. No, 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 no. That's why I always say eventually. So now we've got it. We've got the non-increasing, we've got the limit 0. So therefore, then the original series, n equals 1 to infinity, -1, n plus 1, natural log of n plus 1 divided by n plus 1, what? Converges by alternating series test. And by what we've done in our previous work, we would get divergence. That is, this would not converge absolutely. So we can just say from previous work, when we were doing the comparison test, from previous work, the series converges conditionally. The idea here is that now we have the same kind of setup like we had before. We just had log of n. That's not going to make any difference. The 1 over n plus 1, that's going to be the integral. We know that diverges, so we can just apply the same results. So this would only be conditional because if you take away the alternation in sign, we already know that diverges from our previous work. So you know, ladies and gentlemen, when it comes to doing convergence tests and things, you really don't know how much, you know, it's like, okay, you have to start writing because you have to start processing the ideas. And just like doing integrals, it may not be completely obvious what you need to do. But here's the thing, you have to start writing and you have to, you know, kind of make your way through it. Lots of times on the test, I'll say, prove that the following series converges, and I will say, use a particular test. Now, a more free problem would be prove convergence or divergence. And then you're, you know, at whatever will you have, you can say, well, I'm going to use this test because it makes sense to apply. So it's just like doing integrals. If I specify a particular technique, I want to see it. If I don't, then you can use the technique that you choose. So when it comes to doing series, we pretty much think we're doing the same thing that we did in our previous work. So now what I want to do, ladies and gentlemen, is use one of the error estimates that I talked about and show you how simple it is. When we get to power series for some of our friends, like sine and cosine, they're going to be alternating series. And then, of course, we can use this particular error estimate much to our happiness because it's easy. So let's do an example of that. So in this particular case, it says determine n. So in this case, I'm not going to say, okay, we'll use this many terms in your partial sum to approximate the alternating series. In this case, I'm going to say, you tell me how many terms we need for a specific error. So determine n so that the error is less than 1 over 1,000. So this way, maybe you're doing a project and your boss says, okay, 1 over 1,000 is fine. You know, it could be less, but let's be safe. We don't want the component to fail, or maybe you're working on forces on a bridge and you want to be, you know, extra safe or whatever. So, for instance, here's the series, and of course, if we're going to use the estimate, we need alternating that we already talked about and proven. So we have n equals 1 to infinity, and we have -1 to the n plus 1 divided by 2n cubed minus 1. So now when we look at this, we see in this particular case that the a sub n is 1 divided by 2n cubed minus 1. That's the positive term sequence. Now, what we want to do is use theorem. So all we have to do is just kind of state it, and it tells us exactly what we need to do. So we can say in this particular case that the absolute value of the remainder in this particular case will be no bigger than what? The first neglected term. So the first neglected term is the a sub n plus 1, right? We proved that. After we factored the -1 to the n plus 2, then we got the alternating and used the non-increasing. This was the upper bound. So now we just say, well, if that's a sub n, we just replace n with the uppercase n plus 1. So we have 1 divided by, in this particular case, 2 times n plus 1 quantity cubed minus 1. Again, some of the arithmetic we're doing is very simple, but it's more mature because we have to set it in motion. The problem doesn't just say, well, do this, do this, do this, and you're done. We see in calculus that a lot of what we do has to do with us going out on a limb and taking an educated guess, and then hopefully keeping our fingers crossed that that educated guess about convergence or lack of it proves to be correct. So now we want this to be less than 1 over 1,000. So just to reiterate what we're doing here, remember that when we are considering error estimate for an alternating series, it will be no bigger, given the particular n, than the first neglected term. And certainly in most cases will be much better, okay? So when we do this, we're actually covering ourselves pretty well because all we can do is get an upper bound. It's not going to be exact. So we can get an upper bound and just at least rest assured that we have at least this or maybe even much better. So now, of course, if and only if, these are all positive terms in the sense that this is not 0 for any n. So, and of course, maybe n is 5, 6, 7, whatever. So now we reciprocate. So everything's going to flip around. So we have 2 times n plus 1 cubed minus 1 will now be, in this case, greater than 1,000. So when you look at this, you're thinking, okay, well, this is an inequality. This is now we're back in college algebra. So we have 2 times n plus 1 quantity cubed, add 1 to both sides, is greater than 1,001. Now, at this point, you can do some estimates. You know, a lot of times you can just try values of n to see what works here, and that's certainly a good way to do it. But when you think about it, we can also do estimates by actually solving. So let's apply the cube root function, which is an increasing function, to this inequality, of course, after we divide by 2. So we have n plus 1 cubed is greater than 1,001 divided by 2. So that's just 501/2, right? Okay, so now let's apply the cube root, which is an increasing function. So we get n plus 1 is greater than the cube root of 1,001 over 2. And then, of course, we can solve. So we have n is greater than 500. I'll write it out this way so it's more meaningful to you. 501/2 and 1/2 to the 1/3 minus 1. So now when we look at this and we think about this, we can think about some simple numbers here. So here's a simple way to do this. We think about some cubes. So let's just think outside the box. So 7 cubed, in this case, let's see, I wrote some stuff over here. Let's see, what did I do here? I did 7 times 50 minus 1. This is 343, but at the time I was just doing this like I do in lecture. So this is going to be what? 350 minus 7, which is 343. And then, of course, 8 cubed is just 8 times 64. So that will be, that's going to be 512, right? So that'll be 60 plus 4. So this will be 480. And then, of course, 4 times 8 is 32. So that gives us 512. So now we can see here that we can bound the 501/2 with these two numbers. So this implies that 7 cubed is less than 500. I mean, this is very elementary, like I've been doing, just to give you some extra practice. And so now if you think we can do cube roots, so 7 is less than the cube root 501/2 cube root less than 8, and then we can subtract 1. So 7 minus 1 is less than 500/1/2, 1/3 minus 1 less than 8 minus 1. So now when you look at this and you think about this, this gives us, say we've got a 6, 500/1/2, 1/3 minus 1 here. Okay, so this is kind of like the no man's land. We need the first integer that's going to work. This number is falling between 6 and 7. So we need the first integer that will work, and that'll be 7. So this implies, again, we don't want to take a number between 6 and 7 because our ends must be a positive integer or a natural number. So this implies take n equals 7. So when you look at this example, here's another thing you can do. I don't care if you got to this point and said, okay, well, I'll just use my Google calculator and see what I would get. A lot of times I like to do the construction that's very similar to the type of algebra that we do in our problems to give you extra practice. So you can see here that if we're looking for an error of less than 1,000, we need a partial sum. So this basically says use S sub 7. This basically says use a partial sum with at least 7 terms. So now, of course, we could use, 1, 2, 3, up to 7 with this particular generating sequence with the alternating sign. So this is where you can see that when it just comes to adding numbers and things, this is where the computer side of convergence came into big light. Because as you do engineering projects and you do science projects and things, you now can, with the mathematical theory, produce a sum which is mathematically legitimate. I mean, if you just start by adding up some terms and saying, well, this will do, that could really be disastrous. So you have to be able to look at the particular series and then say mathematically, if we need this error, we're fine. So another thing that you may also notice here is that when you look at this particular term, clearly the limit is 0. And then we could use the same simple inequalities here, not having to use fancy calculus, that this actually is non-increasing. So the thing is, we have to start with a series that converges. So that was tacitly assumed. When you do these problems with the error, you don't have to do a twofer. I mean, I'm not going to ask you to do an error estimate for a series that doesn't converge. That would be wasted effort and simply absurd. So when you do this, you don't have to say, oh my gosh, do I need to first see that this converges? That'll be the assumption. And probably the best way to do it is consider the convergent alternating series, okay? So that would kind of put your mind at rest. You're thinking, do I have to start over with this? No. So anytime you're asked to do a a type of error estimate, you can assume that the given series is by hypothesis convergent. That again, that's like giving you 10 equations on a college algebra test and none of them have solutions. I mean, that would certainly be valid, but I don't want you to think that you have to actually prove the convergence here. So when I stated the theorem about the error estimate, ladies and gentlemen, the assumption is that we start with the convergent series. So what I want you to glean from this particular lecture today is that the comparison test utilize what we already know, the geometric, the p-series, the integral test, okay? And so you're thinking as we move through, those are pretty specific types of tests, positive term series. So we just basically have to focus on the positive term series that we utilized before. And then the limit comparison test does similarly. And like I said before, most students like the limit comparison test better, but you may find that you are just the opposite of that. And then of course, with the alternating series, we have a test that again is particular to this particular study of calculus with Dr. Larson's textbook. And again, it has a very interesting set of hypotheses. We've got this a sub n, which is this positive nth term, and then this plus or minus thing that just kind of is like a lights on, lights off, lights on, lights off. And we focus on the a sub n, and we say if it's going to be the alternating sign, we need a sub n to have limit 0 and be non-increasing. So that's kind of odd, but we see that that's required, at least the non-increasing part, if we need an error estimate. Now just remember, again, as you work through all of these tests, we are doing the standard test. You will come up against other types of tests as you continue to study mathematics, and they will be wonderful tests. But again, we're starting with the most conventional test, and then as we need, we might branch out. So if you take a more advanced course in analysis at the university, or you take an advanced course in partial differential equations, then you will see other tests. But these are going to form the bedrock of what we do with power series. And that's really the goal of this chapter. And then of course, once we're done with this, we'll do polar coordinates, parametric equations, and lots of fun stuff. I'll say it's fun, but then it'll get difficult because we have to use a lot of trig, and that's always a challenge for any calculus student. But again, on Wednesday, I will do some review problems and just cover some ideas that you will have for the test. Again, if it's boring, I apologize. This is just a way to give you some additional insight. You may know everything already, and that's fine. I know you work hard, but just remember that I will be looking for complete logic. Okay, do not utilize any outside sources. You can use your notes. You have access to the Blackboard information, which is fine. And again, this is an online test, and so I can't be there to say, okay, do this, do that. But do not use fancy calculators or computer algebra systems. If I see evidence of that, I will mark off, and I'm at the point now where I don't want to see it anymore. It is fraud. It is academic dishonesty. And when I teach, I try to show you the techniques that I consider to be the appropriate ones. So again, little bit of, Professor Ron, has to be, focused about how we do things. That's so that your grades mean something. I want your grades to be legitimate. I want you to have grades that mean something. That's very important to me, and it should be important to you. Okay, so thanks for your attendance today. I hope you enjoyed this. I, I like all aspects of math, but I think the infinite series and the convergence really helps you to grow mathematically and makes you more into a mathematician. It just kind of elevates your understanding. So I'll send out invitations for my office hours, conference hours. So if I see you then, fine. Otherwise, I'll see you on Wednesday morning to do some review problems. Everybody have a great day, and thanks again for your attendance.